out was roughly 30, and then we increased our difference by 40, even though we increased the frequency by 50%. Or we increased the error by 30% when we increased the frequency by 50%. And what the heck, let's just do the next one.
This is what 605 sounds like.
It sounds exactly what this was producing. Nailed it.
So that'd be 2/5 L for this.
Not 2/5. So the first one, it's 2L, then 2/2, then 2/3.
It would be 2 or 4 tabs.
Okay, it'd be 2/4 or a half.
Yeah.
So the wavelength for the fourth harmonic.
Oh,
Wait, so what are we adding on that? Or what's the difference between each? I must not have written it down right then. If the first one we're adding a half,
We add a half wave every single time. So we have a fixed length. So L, we start out with a half of a wave, then it's 2/2 waves, 3/2 waves, 4/2 waves, 5/2 waves. And then
okay.
define the wavelength that's the reciprocal of each of those. So the denominators become numerators, and so the numerator stays 2.
Okay.
So this should be half of L. And so the frequency we should hear, assuming our incredible predictions here. So F of 4 would be 807.6 hertz. All right, ready to challenge physics?
Well, it was like oscillating between like several different frequencies, but the middle of that was about 744 hertz. That was,
that's 744.
I guess that was the Doppler effect, because it being further and then closer.
Possibly. I was trying to swing it this way, but to avoid that.
That's 807.
All right, I can definitely hear a difference between those two frequencies. So now we're 60 something off. So we're worse there. I want to check out the Doppler thing, the higher frequency. Verse. They sound the same?
Pretty much.
Okay. Then in the future, when students complain, I can say, listen, Benjamin and Patrick said no. All right. At this point, you can do all of the Rube Goldberg test. Questions? All right. Why don't we take a break here? Then we'll come back and wrap up the wave stuff, talk about due dates, and potentially look at the relationship between temperature and kinetic energy. So we've talked about when a wave hits a fixed boundary, it will reflect. If it's a free boundary or free end, it will also reflect, just the wave reflects differently. But when it hits a boundary in general, some of it will reflect and some of it will be transmitted into the new medium. And so the question we're gonna take a look at right now is what happens when it hits the new medium? So I'm gonna just present a boundary right here, boundary. Is it D-R-Y or D-A-R-Y? Boundary or boundary?
I think there's an
You wanna look it up?
A. Yeah, there's an A. It's A.
It's A, all right. So as a wave is coming in, so just imagine, I think thinking of it as water waves sometimes helps. But I've got, if it's sound, I got high pressure coming in, got a high pressure wave followed by another high pressure wave followed by another high pressure wave. Assume it's a constant frequency, just to make life simpler. So I have this wave coming in at some set frequency. So we assume that the frequency, therefore the period, are constant. And as it hits the new boundary, it's not necessarily going to be traveling the same speed as it did before. We've seen it with the case of a line that the speed is equal to the tension divided by the linear density. As a general rule, the speed of a wave is equal to some force term divided by some inertial term. So the more mass or whatever the inertial term is you're dealing with that you have to move, the slower the speed's going to be, the greater the force, the higher the speed's going to be. So this is a generic equation for pretty much all waves, and specifically for along what we can pretend is one-dimensional. We have this. So as it hits it, my speed is going to change, but my frequency stays the same. Therefore, my wavelength will also change. So when the wave first hits, it's like that, and then when it hits again, and that's to sort of represent the fact that the speed of the wave is not, that the speed of the wave has changed. And in this particular case, it slowed down when it hits the new medium. These peaks, the distance from peak to peak would be the wavelength. So I'm going to call this boundary section 1 and section 2. So this would be the wavelength of 1. That would be the wavelength of 2. Well, if I set up the right triangle here, since it's traveling perpendicular to the wavefront, here and here, I have a right triangle there and I have a right triangle there. I know this distance right here is common to both of them. So I call this theta 2. And call that one theta 1. That's the wavelength of 1. And that is the wavelength of 2. And then I've got this length right here, which I'm just going to call lowercase l. It is the hypotenuse in both cases. So I know that the sine of theta 2 is equal to the wavelength of 2 divided by L. And the sine of theta 1 is equal to wavelength 1 over L. L is the same for both. And so L is equal to wavelength 2 over the sine of theta 2. Which equals theta 1 over the sine of theta 1. I know that the wavelength is equal to the speed over the frequency. Bless you. So if we make that substitution, I have the speed of 2 over the frequency sine theta 2 is equal to the speed within section 1 over the frequency times sine theta 1. I didn't put a subscript next to the frequency because the frequency is the same in both situations. It cancels out. And we end up with whatever form you want to put it in, but sometimes written as V2 sine theta 1. That's supposed to be a 2. It's equal to V1 sine theta 2. And this is known as Snell's law. And so this is a characteristic of a wave. So a wave is a new boundary. So if you're using a light wave also, it obeys this. And you can see that if you shine a, well, actually, if you look at anything in a body of water, if you look at it just right, that it appears bent. You got the part above the surface and part below the surface of the water, like a pencil in water, or a pen. Not a dramatic effect there, but hopefully you can see that it doesn't look like it's 100% straight there. And that also obeys Snell's law. Now, I first took calculus. I took calculus before I took physics. And so this was the following problem was in a calculus class I had. The shore, the beach, the ocean. You are here. Someone needs help right here. Person needs help. Now, if you run straight to the water here and then swim out to the person, probably not the fastest way to get there, because this distance, you can travel faster on the beach than you can swim. So the speed on the beach is greater than the speed in the ocean. If you stay more time on the beach, that's not necessarily the fastest way either. That there is actually an optimum point which you would run to, and then to get to that person as fast as possible. So let's analyze it. And as you might expect, it obeys Snell's law. We will keep those. Nope. That. All right, making sure I keep the same notation as I have in my notes. The distance, what we'll call the vertical distance from you to the person is y, and the distance, the horizontal distance is r. Scratch that, not y, L. We'll make this distance y and that distance x. So therefore, in this triangle right here, you get x, try that again. This distance is r minus x from here to here, and this distance here would be L minus y. So we're gonna come up with an equation for the time it would take. And then we're gonna optimize it. I know that I'm traveling at a constant speed on the beach, traveling at a different constant speed in the ocean, but assuming that the speed is constant for at least each of the seconds. I know that my displacement is equal to speed times time, or distance is speed times time. we are assuming we're traveling in one direction here. And therefore time is just the distance divided by the speed. Well, the distance it's going to travel is just the hypotenuse of these triangles. So time is going to be equal to the square root of r minus x squared plus l minus y squared over how fast you can run on the beach, v sub b, plus the time you're in the water, which is just x squared plus y squared, over the speed in the ocean. And I'm trying to figure out where's the optimum spot here. In other words, what is this value of x in terms of our variables here? How would you find the optimum time? How would you minimize the time with respect to where you actually hit the ocean? Or in general, how do you do an optimization problem?
Finding the minimum or maximum,
Okay.
which involves taking the derivative and finding where that equals 0.
Yes, and that's what we're going to do. So because x is setting the variable there, we're going to do dt dx. That's what we're trying to figure out, is where do we hit the ocean. So we take the derivative with respect to x. Well, the speed I run on the beach or the speed I swim in the ocean does not depend upon x, it just depends upon the medium. So I'm taking the derivative of this. So what is the derivative of this right here? And I'm going to put this into exponential form. Wait for one of you just to chime in. Jane will start with the outside, work your way in.
1/2 r minus x squared plus l minus y squared to the -1,
The negative
1/2.
-1/2. Okay.
Do we need to multiply by negative somewhere? Inside? Or,
Well, eventually we'll get a negative number inside, but
because it's negative x squared, does that need to multiply on the outside? Or have we just not gotten there yet?
we were, all right. So we did the big thing. Now we work our way inside. So what's the derivative of this?
Alright.
2r minus x.
All right. So I got 2r minus x, and now work our way in,
Times the -1.
and then this.
This drops out because of
All right. Plus 1 over speed in the ocean times
1/2 x squared plus y squared times 2x.
There we go. All right. Equals 0. So what I'm going to do is I'm going to consolidate. This side over here is a negative. This is that -1. I'm just going to add it to the other side. And I want some room. So I have, let's say the denominator, r minus x squared plus l minus y squared with a 2vb. And then in the numerator, 2r minus x plus, equals that over there, which is, the 2's will cancel out, so I'm left with, that should be to the negative 1/2. X over square root of x squared plus y squared. These would cancel out on the other side as well. Oh, and I lost my VO. Those two cancel. All right. We could go through and actually solve for the value of x, but there is a shortcut here, which I will employ. Let's look back at our triangles here. This length right here, this is the square root of x squared plus y squared. This length right here is the square root of r minus x squared plus l minus y squared. What is x divided by the square root of x squared plus y squared? Looking at this triangle here. X divided by that.
What's the sine of that bottom angle?
All right, so why don't we label this theta sub O? So this is just sine of theta sub 0 over v sub 0. And on the other side, we have r minus x divided by that.
Just cosine of whatever that angle is.
This one here? Yeah, let's take this one though. Yeah, you're right. But since we're taking the angle here with respect to the vertical, let's take the angle here with respect to the vertical.
Oh, right.
And so that is the sine of theta sub beach over v sub beach. So that's v sub O sine theta b equals v sub b sine theta O, which is what we have right there. Just different subscripts. To me, I thought that was very interesting that the Snell's law